Okay, thank you, Andreas, for the introduction and for the comments. So thanks for organizing all this stuff, and can believe that's quite a lot of work. Our next plenary talk for today is by Heping Wang. Heping did his PhD in 1996 on approximation and quadrature formulas on function classes with mixed smoothness. And since then, he has quite a lot of work in this direction, also in a more general context, and often with respect to a randomized situation, a randomized setting. And I think he will tell us something about this also now. Let me lastly announce that last year he won the IBC Award for Achievements in Information-Based Complexity, which might be seen as a kind of a proof that this is interesting, at least to some of us, in a big way. Okay, Heping, the stage is yours. Thank you very
much. Thank you for Mara for nice introduction. Thanks for organize to invite me to give a talk. My talk and the title of my talk is Tractability in Randomized Setting. This work is partly joined with Wang. In this talk, we outline the outline of the talk is separated in 5 parts. As first, we give introduction, and in section we give preliminaries, and in section 3 we give the equivalence of tractability for lambda R and lambda stand in a randomized setting. In section 4, we give the tractability for uniform approximation of tensor product smoothness space. Finally, we give conclusions. Introduction. In recent years, there has been an increased interest in Monte Carlo methods. Monte Carlo method is also called randomized methods or stochastic methods. Compared with deterministic methods, Monte Carlo methods have much superiority for computation of integrals and for certain function approximation problems due to they can speed up order of convergence. Monte Carlo methods can also be used to improve tractability in the information-based complexity theory. In this talk, we consider tractability in randomized setting in the information-based complexity theory. We study multivariate approximation, APB, where APBD is a compact embedding operator. FD is a reproducible kernel-Hilbert space, function space on DD. GD is a Banach space, function space on DD. DD belongs to RD, and dimension D is larger or even huger. We use lambda R and lambda STD to denote the class of all continuous linear functions and the class of all functional values, the standard information, respectively. We consider information operators. ANF is defined as follows, where Li belongs to lambda, lambda belongs to lambda R or lambda stand. Note that lambda stand is belong subset of lambda R. The class lambda stand is much smaller and much more practical and is much more difficult to analysis than the class lambda R. Hence, it is very important to study power of lambda stand compared to lambda R. We consider the algorithms that use finitely many information evaluations ANF. The approximation error of algorithm can be defined in various case settings, including worst case setting, average case setting, probabilistic case setting, and randomized setting. In this talk, we consider only randomized setting and compared worst-case setting. There are two error criteria, absolute error criteria and normalized error criteria. Sorry. For given error threshold, epsilon belong to 0, 1. The information complexity n epsilon d is defined to be the minimum number of information evaluations for which approximation error of some algorithm is at most epsilon. Tractability is an aim to and study how information complexity n epsilon d depends on epsilon and d. It was introduced by Wang in 1994. There are two kinds of tractability based on polynomial convergence and exponential convergence. The algebraic tractability describes how information complexity n epsilon d behaves as a function of d and epsilon minus 1. And while the exponential tractability does as 1 of d and 1 plus 9 epsilon plus minus 1 minus epsilon. The existing notions of tractability mainly include strong polynomial tractability, polynomial tractability, quasi-polynomial tractability, weak tractability, ST weak tractability, and uniform weak tractability, and the cause of dimension nullity. In simple words, SPT means n epsilon d does not depend on d, while PT means n epsilon d is a polynomial increasing in d. ALG WT means n epsilon d is not exponential dependent on d and minus epsilon. The cause of dimension indicates n epsilon d grows exponential in d. Sorry. The standard reference about the tractability are follow three books. There are many papers investigated exponential tractability in recent years. In this talk, we study two multivariate approximation problems. First, we discuss approximation in randomized setting with error measured in weighted L2 normal, and discuss equivalence of various solutions of algebraic and exponential tractability for lambda STD and lambda R in the randomized setting. We show that on the normalized or absolute error criteria, the power of standard information for tractability is the same as that of general linear information for all notions of tractability. Second, we investigate uniform approximation of functions in tensor production reduced kernel Hilbert space use lambda R in randomized setting and show that it is polynomial tractability tractable on the normalized error criteria. This is contrary to deterministic worst-case setting, in which uniform approximation problems of tensor product space suffers from cause of dimensionality. Now we give some preliminaries. First, we give worst case city. For D belong to Z, let SD from FD to GD be a bounded linear operator between two Banach spaces, the so-called solution mapping. We consider methods then use continuous linear functions or function value on FD. We aim to approximate SD for input FD1 belong to FD by deterministic approximation methods of AND. F is defined as this. Where Li belong to lambda. The mapping ANFD called information stand for process of getting information about F, and the mapping F phi AND represents the computation process and generate output AND as approximation to SDF. Usually, the input as tilt FD is chosen as the uniform of BFD of FD. The information ANF is called non-adaptive. If ANF is this form, where A and L cap belong to lambda are fixed and do not depend on F. The information ANF is called adaptive if the choice of functionals A cap may depend on previous obtained information. If information A is non-adaptive and the map phi and D is linear, then we call it deterministic method A and D is linear. Otherwise, we call A and D non-linear. By this set, we denote the class of deterministic linear methods with the cardinality unity less than n, and L cap belong to lambda. The broader class of non-linear methods with cardinal n shall n is denoted by this. The worst case error of a deterministic method A and D is defined as this. The n minimum worst case error is defined by this, where the infinity is taken over all A and D belong to this set. For n is equal to 0, we use A and A0D is 0. We obtain the so-called initial error E worse than this is defined as by SD, the normal of the operator of SD. For D belong to N, now FD be a reproduce kernel Hilbert space of D dimension functions defined on DD. GD is defined as this, and SD is approximation. Approximation is a compact embedding operator. Assume GD is defined as this. Is value than E was in D lambda R depend on eigenpairs of lambda KD, EKD of operators WD is equal to this. Where lambda D is arranged as lambda KD is arranged as in non-increasing order, and EJD is an orthonormal basis in FDT, and satisfy this equation. From NW1, we get the minimum worst case error is this. and is achieved by optimal linear algorithm defined as this. That is, this worth is defined as this. Without loss of generality, we may assume that all eigenvalues are positive. We set eta kt is defined as this. We remark that EKT is an isonormal basis in FTT. And eta kt is an orthonormal system in GT. And for F belong to FD, S ANT shin. The star is defined as this. Now we get the randomized setting. The randomized methods, also Monte Carlo algorithms, are understood as this. Measurable mappings as this. Where this is and this denote Borel sigma algebra of FT and GT respectively. Omega sigma p is a suitable probability space, and for any fixed omega belong omega, and omega is a deterministic method with cardinality and is a f. The number n f omega may randomize and adaptive depend on the input, and the cardinality of n d omega is defined by this. If for each fixed omega belong to omega, and d is deterministic linear method with fixed n, then we call and d omega is a randomized linear method, denoted by this. The class of all randomized linear methods with cardinality less than n, and similarly this set. We remark that a deterministic method may be viewed as a randomized method that is independent from omega belong to omega. Hence, this set can be regarded as a subset or subclass of this set. The randomized error or randomized method A is defined by this. We defined a minimum error or problem SDD as error of optimal algorithm is defined by this. Where diamond belong to worth or rank, and star belong to linear or nonlinear. We use this, the Monte Carlo error or randomized error, and E was this, the worst case error or ST. We have the following ways. Usually, the nonlinear, this quantity may be defined as this. We remark that in deterministic, the aim minimum deterministic error is defined, use linear algorithm is just as n plus 1 approximation number. And a minimum number, this set is just the n plus 1 Gelfand number. This is also called the Monte Carlo approximation numbers of ST. There are many papers devoted to study Monte Carlo approximation and relations with this. The information complexity can be studied using are the absolute error criteria or normalized error criteria. For diamond belong to this, star belong to this, and lambda belong to this. We define the information complexity as this, where the CRT is defined by this. We remark that the initial information are all equal to this. Since lambda stan is a subset of lambda R, we have this. Now we get notions of tractability. First, we introduce all notions of algebraic tractability. We give this cell. In the diamond setting for the class lambda and for error criteria star, we say APP is an algebraic strongly polynomial tractable if there exists C and non-negative P such that this. The explode is defined as infimum of P. APP is algebraic polynomial tractable if there exists C and PQ such that this. There are also QPT such that the information complexity satisfies this inequality. We also can define the exclusion of this. APP is an algebraic weakly tractable LGWT if the information complexity satisfies this inequality. APP suffers from cause of dimensionality if N satisfies the following inequality. If APP suffers from cause of dimensionality, then APP is intractable. There are also the notions of LG UWT and LG STWT as follows. We have the follow relation. If the N minimum error discards faster than any polynomial and is exponential convergent, then we should study tractability with epsilon minus epsilon being replaced by 1 plus 9 minus epsilon, which is called the exponential tractability. Recently, there has been many papers studying exponential tractability. In the definition of LG-SPT, these notions of LG tractability, if we replace by this, we can get the definition of EXP-SPT, EXP-PT, EXP-QPT, EXP-WT as this. Now we get the smoothness function space. In what follows, T denotes torus, that is this. TD stands for D-dimension torus. we encrypt TT with normalized Nobel space measure this. Consequently, EIKX is as a normal basis in L2TT. F hand F is the Fourier coefficient of a function F. Let W be a positive function on ZT, satisfied for all K. But satisfied for all K, WK is this. We can define smoothness function space. FTW is defined by this. Obviously, FTW is a Hilbert space with inner product as this. And also normal basis, eta KT is defined as this. We remark that the FTW is compactly embedded into L infinity TT and CT if and only if this. In this case, FTW is a reproducible kernel Hilbert space with reproduced kernel this. These functions are real functions. Often we use normalization of reproduced kernel K, such as KXX. This is equivalent to this. If all is less than Q and is equal to infinity, then FTW is compactly embedded in LQTT. Now we can, if WK is defined as this, and WK from 0 to infinity is a non-decreasing positive sequence satisfies this, then FTW is called tensor product Hilbert space. Superficially, subunit space of dominating mixed smoothness is a tensor product Hilbert space with this. We also have the embedded in LQ2TD the condition if and only if S is equal to this inequality. We also consider the embedding operators this. In this case, we consider approximation problem this. Is seen WK minus 2 eta K are eigenpairs of operator W this. We also arrange it as lambda KT are eigenpairs of the operator W as this. In this case, we obtain that this. This is included in the subsection 2.1. We also have the inequality. We remark that in deterministic worst case setting, linear methods are always optimal. Always optimal. We have the following inequality, and inequality. We also obtain the worst case setting as this, and randomized setting as this, These results are also obtained from these 3 papers. Now we introduce the main results. First, we give the equivalence of tractability for lambda R and lambda stan in the randomized setting. We recall that the class lambda stan is much smaller and much more practical and is much more difficult to randomize than the class lambda R. Hence, it's very important to study power of lambda STD compared to lambda R. There are many papers devoted to the study of this field in different case settings. See the following results. The first 5 papers are devoted to the power of lambda STD compared to lambda R in the randomized setting. These 5 papers. And these papers are devoted to the power of standard in the worst case setting. This paper and this paper are devoted to the power of standard in the randomized setting, in the average case setting. In this talk, we invested in equivalence of tractability for lambda R and lambda STD in the randomized setting. It follows from NW set and this case. By the above inequality, we can get the equivalence of various notions of tractability for lambda R in worst and randomized settings for the absolute and normalized error setting criteria and the exclusion of LG in the worst and randomized setting are all same. Therefore, it suffices to discuss the relation between in-range stan and in worst lambda R. The first important progress upon relation between in-range lambda STD and in-worst lambda R was obtained by this paper. They construct integrated Monte Carlo methods to get about the inequality. That shows the power of in-range STD and in-worst lambda R are the same, and establish the equivalence of SPT and PT LG for lambda R and lambda ST for normalized error criteria in randomized setting. The book NW4, NW3, and Craig refined about randomized algorithm and show that GRANG is asymptotic of same order as this. Given that G was R, lambda R is recognized decrease. However, the obtained relations are heavily dependent on initial error and are not sharp if G was lambda R is exclusion convergence. If the nodes X1, Xt draw independently and identical distributed according to gain approximation measure, then the samples on nodes X are called random information. We remark that the randomized information are often optimal or linearly optimal for approximation and integration of subnet space in the worst case and randomized setting. See here these papers, four papers. using the random information and the least squares methods, we can obtain relations between in-rank STD and inverse lambda R. The others can use randomized information, satisfy some conditions, and least square methods to obtain inequality beyond this and this. They remarked that using the weighted linear squares method can improve the above inequality. We use method proposed in this, then combine the proof of KUV and with weighted linear square methods used in CM to get improved inequality beyond this and this. The contraction of randomized algorithm is as follows. We keep notions of subsection second to 1. For m belong to natural number, we define HMD and omega MD as follows. Where eta JD is an orthonormal system in GD, then omega MD is a probability density function on DD. And this, we define the corresponding permutation method mu MD defined as this. Where A is the Borel subset of DD, we use convention this. Then eta JD tier is a normal system in L2 DD mu MD, where tiered eta JD is defined as this. For X belong to this, we use follow a matrix defined as this, and HM is defined as this, where A star is the conjugate transpose of a matrix A. Now let MA satisfy this inequality. X1, XA be independent, identical attributed sample points from DT. Then are distributed according to probability measure UMG, and AM tiered HM be given by 1. If the sample points X satisfies this inequality, then we discarded these points and resample until the resample points satisfy this. That is, we consider conditional distribution given the event this. And the conditional expectation is defined as this. If HM this inequality holds for some X, then LM have 4 rank. The algorithm is a weighted least square estimate. Is defined as this. Which has unique solution, where VM is defined as eta 1D and eta MD the span. We obtain the following results as obtain this. From theorem 1, from above results, we get this. Compare with the results in 2 papers. Our inequality does not depend on initial error, and are almost sharp if E was in E is exclusion convergence. However, if E was lambda R is recognized decreasing by our inequality, we can only obtain is this quantity is and most asymptotically out of this, where n is underneath of this. Recently, could further obtain the following optimal results. Now we return to tractability. Based on theorem 1, we obtain two relations between information complexity and lambda R for this. We have the following inequality. In the randomized setting, for normalized error criteria, NW3 give equivalence of this and show the exclusion of LG SPT and LG QPT for lambda R and lambda STD are same. For absolute error criteria, NW3 also give equivalence of LGPT, QPT, WT for lambda R and lambda ST on some conditions on the initial error lambda 1. The Wang and Worsky post the open problems 19.8, 0.1 and NW7 with asking whether above conditions are necessary. Based on theory 2, we obtain equivalence of for absolutely without any conditions, which means the above conditions are necessary. This solves the open problem, the three open problems. We also obtain equivalence of LGUWT and LGSTWT and various solutions of EXP tractability for lambda R and lambda ST for normalized and all absolute error criteria without any condition. This gives enormous complete solution in open problem 100 in NW7. Combining with the previous results, we obtain the following corollary. This means the power of STD is the same as lambda R in the randomized and worst case setting. Now we give another main result of this talk. We give the tractability for uniform approximation of tensor product smoothness space. We consider approximation of tensor product reproduce kernel Hilbert space FDW with normalized reproducer kernel in LQ. In this case, we assume that WK is defined as this, and WK is a non-degressive positive sequence. Satisfy this. This is a normalized condition. And this inequality for some alpha belong to 0, 1. In this case, we have the initial error have this. So the normalized error criteria and absolute error criteria coincide. In the worst case setting, Cruz shows that in K, then the usual tensor uniform approximation problems suffer from cause of dimensionality. That is, the information complexity grows explosion in D. So in fact, we have the following inequality. through the uniform approximation of problems of tensor product space suffer from cause of dimension unity in the worst case city. Consider uniform approximation problems in Kurbov space, which are periodic tensor product reproduced kernel Hilbert space with smoothness R is greater than 1/2, and on the normalized error criteria, we use also shows that for above problems, the Monte Carlo methods can break cause of dimension unity. Now have polynomial tractability as follows. Where C is a constant independent of D. This means the above uniform approximation problem is a polynomial tractable in the randomized setting and suffers from cause of dimension unity in deterministic worst case setting. Note that Cruz use the probability methods in this paper. The method is not suitable for user tensor product uniform approximation problem. We construct the Monte Carlo method that extend above results from above Kurbov space to the uniform tensor product space FDW satisfies 3. And show that above uniform approximation FDW is polynomial tractability in the randomized SCT. The randomized algorithm is constructed as follows. First, we give the construction of error estimates of linear Monte Carlo algorithm. We first use the follow position, which follows from this paper, and is a key component for Monte Carlo approximation of Hilbert space function by linear information. This approximation originates from math and have been intended further includes in this paper. Fundamental Monte Carlo methods. Suppose that SH from 2D is a linear rank M operator from Hilbert space H into a Balach space G, and let constitute an orthonormal system in H such that this. We use randomized rank N methods as defined as this, where we choose randomized function Li omega and corresponding random functions Gi omega is defined as this. Here, Xij are independent standard Gauss random variable. Then we have this inequality, where Xij is a dependent standard real Gauss random variable. Now at it be also normal basis in FTW, and for any x we have this. We have the expression of f as this. Now we did so as f is defined as the plus of 3 parts. The sum of 3 parts. Now we construct the randomized linear methods with cardinality 2n. For when this, we define a n m omega f is defined as this. Where this. So the algorithm AN omega is the sum of Fourier partial summation operator SAN and the Monte Carlo algorithm Y formation Monte Carlo approximation method for SAN from above approximation. Similar algorithm is constructed as this. We obtain the following estimates on inspection number with the dependent standard Gauss random variable CK defined as. We have this equation. From this approximation tool, we get from this equation, and we also choose space XM satisfy the following Minkowski inequality as this. Then we get the main result.
Heping, sorry to interrupt you. You haven't read the chat, so you're basically at the end of your time. So please hurry up.
Yeah. Then we have this. So we have this inequality. And for LQ is equal to L infinity, we have this. So we consider we have the results. Suppose that WK belongs is equal to 1 and this. For some alpha belongs 1, then we have this inequality. This and this inequality. This estimate means that this and this. It follows that in randomized case setting, uniform approximation problem of tensor product space are polynomial tractable, and LQ approximation of tensor product space are strongly polynomial tractable. Space frequently under normalized error criteria, the uniform approximation problem I infinity in randomized setting is polynomial tractable. We know that in deterministic case setting, uniform approximation problems of tensor product space suffer from cause of dimensionality. Our inequality is not sharp compared with the close paper. Finally, we give the conclusion. In our talk, we give 2 problems. For weighted L2 approximation problem, we obtain in randomized setting for lambda and lambda t for normalized or absolute error criteria. The power of lambda STD and the lambda R is the same as that of lambda R for all notions of explosion and algebra tractability without any conditions. We show that in randomized setting, use lambda R, uniform approximation problems of tensor product smoothness function space are polynomial tractable, while in the worst case setting, the problem suffers from cause of dimensionality. For uniform approximation problems, we want to study the power of STD in the randomized setting in the future. We also want to improve certainty in the future. Thank you for your attention.